Okay, so how do we accomplish this with software? I'll cover three options: Excel, SAS, and R. Firstly, in Excel, the t-test can easily be accomplished using the t-test command. The first and second components are the respective arrays. A1, in this case, is cells B2 through B6, and array 2, which is cells C2 through C6. The third term in the command, tails, we use 2 to specify a two-tailed test. The fourth term, type, describes the various t-test options we've been discussing. Type 1 specifies a paired t-test. Type 2 specifies equal variance, or in statistical parlance is homoscedastic. Type 3 specifies unequal variance, or heteroscedastic. Note that we don't need to specify the unequal sample size option because Excel is perfectly capable of using the correct algorithm based on the numbers specified within each array. In this case, we have 5 values in each array, and it will be using the equal sample size option. Execution of the t-test command, Excel will generate a value between 0 and 1. This is the probability that the observed t-statistic, which is not actually shown during the calculation, could have occurred by chance. A low value, i.e. less than 0.05, has a low probability of occurring by chance, and the two means would be stated to be significantly different. A value greater than 0.05, which is the case in this example here, has a high enough probability of occurring by chance that the two means are stated to be not significantly different. We would state, based on these data, that 5.76 is not significantly different than 7.84. T-test in R. My explanation will be fairly brief since we'll be having more practice with programming in R and SAS in the recitations. In R, we have a range of different options that include unequal variance, equal variance, and the paired t-test. These all include the t.test command. The default option in R assumes unequal variance, which is usually the more conservative option. If we want to specify equal variance, the t.test command has the option var.equal equals true. If we want to use the paired t-test, we can use the paired equals true option. If we only have a one sample t-test, where we're comparing a mean to a specified value, in this case 3, we would specify the mu equals 3 option. For those of you that are programming in SAS, we use the proc t-test. SAS is typically more verbose in its output than other software. And so in the case of proc t-test, when we're comparing variable A with variable B, SAS will generate a range of options by default. So working through this sample output, we can see that we have 10 values for treatment A and 10 values for treatment B. A mean of 4.27 is compared to 5.2. You can skip over this middle part of the output, and we can see here the t-test results. The pooled option is the assumption for equal variances, and as you would expect, has 18 degrees of freedom. That is, 10 plus 10 minus 2 is 18 degrees of freedom. In this case, we can see that the probability of the t-value is 0.4065 is greater than 0.05, and we would state that these two means are not significantly different. If we wanted to see the effect of unequal variance, the effective degrees of freedom have been calculated here as 12.435. We can see this is considerably less than 18, and the required critical t-value, which is not shown here, would be larger. If we go look up here, we can see that the standard deviation for B, 3.3, is quite a bit larger than the standard deviation for 1.4, a variance ratio of 2.4, and most likely significant if we were to look up that value. Both these methods, the pooled and unequal variance, have similar but not identical probabilities, with a similar conclusion to the equal variance that is not significant for either option. We also have the option in SAS for making paired t-test within the proc t-test command. We would use the option paired A times B to generate a paired t-test comparison.